Let's look at just a couple of problems in Chapter 7. So these were series parallel combination circuit problems, and I'm going to highlight a couple different methods you can use when you're analyzing these basic DC circuits. So first we're going to look at the reduce and return method of circuit analysis. Reduce and return is basically where we take this circuit and we reduce those resistor networks down to just one total resistance of the circuit and find our source current, and then we work our way back through those steps. So what I'm going to do is I'm going to start by combining my resistors here and my resistors here. So I'm going to call this resistor A, where I've got 3 parallel resistors. Remember, resistors are in parallel if they're connected on 2 sides, as these are. They're connected on the right and on the left. So the total resistance here, 1 over 1/6 plus 1/6 plus 1/2. And that would be 1.2 ohms there. And for the 8 and the 12 ohm resistors, those are also in parallel because they're connected at the top and at the bottom. So that will, I'll call that RB. And there I have about 4.8 ohms. Now, one of the most important things you can do with the reduce and return method is that you will redraw your circuit at various points. So I'm going to redraw my circuit. This time I have RA, which is my 1.2 ohm resistor. So what I did was I took off the 3 resistors and I put RA right back there. And now I'm going to take off the 2 resistors here, R4 and R5, and I'm going to put RB right there. And that was 4.8 ohms. I didn't do anything to my source. Okay, so this would be step 2, or circuit 2. Now for the last step, I'm just going to combine RA and RB, because that will give me the total resistance of my circuit, and that should be about 6 ohms. 1.2 plus 4.8 will be 6. So the last step, I'm just going to redraw the circuit with 1 source and 1 total resistance. Now, the reason we do this, and I'll call that step 3, the reason we do this is so that now we can step back through our circuit. So we want to find a source current. The 24 volt source sees 6 ohms of resistance. So that means it's going to have to supply us 4 amps of current in order for that to work properly. So this is everything I can do with this third circuit. So I'm going to take my 4 amps and move up a step, and that's the same current that I have here coming from the source. And now I'm going to calculate my voltage drops across RA and across RB using that 4 amps. Notice RA and RB are in series with each other, so they both have 4 amps of current going through them. So VA is going to be 4 amps times 1.2 ohms, or 4.8 volts. And VB will be that same 4 amps times 4.8 ohms, which should be about 19.2 volts. Now let's do a quick little check of ourselves here. Kirchhoff's voltage law says that my 24 volt source should result in these voltage drops equaling 24 volts. So if I have a 4.8 drop that leaves me 19.2 volts, and then I have another 19.2 volts across RB. So KVL holds up as well. And now we can move this information back to my original circuit. So in the original circuit, I sub S is 4 amps, and I'm going to put my voltages in. That would be the 4.8 volts here for V1, and I've got 19.2 volts here for V5. The only thing left I could find is the individual currents through each of my resistors. So let's work on that. Now there are a few ways we could do this. We could use the voltages, because remember this 4.8 volts here is the voltage drop across R1, R2, and R3, because they're in parallel and they have the same voltage drop across them. So I could just take our voltage drops and calculate I1, I2, and I3, because each have 4.8 volts, and then I would divide by that particular resistance of that branch. 4.8 volts divided by the 6 ohm resistor R2, and 4.8 volts divided by the 2 ohm resistor for R3. So that gives me 0.8 amperes, 0.8 amperes, and 2.4 amperes. So I'm going to put that in 0.8, 0.8, 2.4, and notice my 0.8 plus 0.8 is 1.6, plus 2.4 is 4, so my 4 coming in equals the 0.8, 0.8, and 2.4 leaving that node. All those currents come back together, so I have my 4 amps over here. And let's find I4 and I5. Now for R4, the voltage drop across that is 19.2 volts, and I've got 8 ohms of resistance there. So that gives me about 2.4 amperes. And then that same 19.2 volts across 12 ohms gives me 1.6 amperes here. So I've got 1.6 and 2.4, which again, 4 amps coming in, 2.4 goes this way, 1.6 this way. Those come back together on the other side to be 4 amps. Okay, so that's the reduce and return method, where we reduce the circuit in sequential steps to get to the most basic circuit, where we have our T and our source that allows us to find I sub S, and then we work our way back with the information we have found in each previous step. Now I want to look at this bridge network and kind of talk about how we might solve this. If you notice, R1 and R2 are connected over here, but they're not connected on the other side. They've got this voltage source in between them. And then R3 and R2 are connected here, but then they've got that 8-volt source between them on the other side, and they're also not in series because they've got this other path for current. So we have to find another way of doing this. Now, one thing we can do is if the triangle configuration bothers you at all, you can redraw the circuit. So basically this is redrawn here to get rid of the triangle configuration, but it's really the same thing. Here we have a point that's VA, and here VA is more of a straight line, and that's fine. They both have the same voltage at that point, so there's really no problem with doing that. Okay, so if this is better to look at, again, we cannot reduce this down to one resistor the way it is because we've got these 3 sources. However, what we can do is use our Kirchhoff's voltage law and Kirchhoff's current law to analyze the circuit a little bit further. So notice right here, I've drawn a loop in here. If we do a Kirchhoff's voltage law equation for this particular loop And I'm just going to draw it kind of bigger. Notice we know this voltage, we know this voltage, this is the only unknown, so we could solve for that. So let's write our equation for just this particular loop. So I would write this equation as plus 20 minus 5 minus V3 and set that equal to 0 based on the polarities or the directional signs that they have given me, the pluses and the minuses. And if I solve for V3, that means that V3 has to be 15 volts. And since it came out negative, the direction I chose was correct. So that would have to be 15 volts right there. Now, once I know that, I could use a second KVL equation here. I'm going to call that 1. And let's use, let's do a second KVL equation here. Again, starting in the clockwise direction, I like to go from the bottom left corner. And so the first thing I hit is this 15 volts. It's going from minus to plus. I'm going to add that. And then I've got whatever this voltage is across R2. I don't know what the direction is, so I'm just going to guess and put plus to minus and subtract that. And then from here, plus to minus means I'm going to subtract the 8 volts and set that equal to 0 as we get back to where we started. And if we solve for V2, we see that V2 would have to be 7 volts. And it was positive, which means the direction I picked was right. If it were negative, I would just change the direction. So that would have to be 7 volts. And then I can do a third KVL equation right here. Again, I'm going to start here and travel around clockwise. So plus 5. I don't know the direction here, so I'm just going to guess, make it a minus. And then in this direction, I actually have a voltage rise of 7 because we're going from minus to plus in that clockwise direction. So V1 would have to be 12 volts. Again, it comes out positive. Therefore, I chose the right direction that time. Again, if you get a negative answer, all you have to do is change the plus and minus to match. All right, so now that I know all of the voltage drops across all of the resistors, I can find the current through the resistors. I can't use Ohm's law to find the current through my sources because I don't have enough information to do that. But I can find, let's start with I1 right here. I know that it has to be the voltage drop across R1 divided by R1. So that has to be 1.2 amps. So I'm going to draw that in, 1.2 amperes. Let's look for I2. This is R2. So that would have to be the voltage drop across R2 divided by R2. And that's 1.75 amperes. And which direction would that be? Let's talk about the direction. It's we say that the current is going to flow from the positive terminal to the negative of the power supply. However, through a resistor, the current is going to enter on the more positive side and leave on the more negative side. So that's the 1.75 amperes right there. And then let's go ahead and find I3 while we're using our Ohm's law tool here. So R3 is right here. We know we have 15 volts drop across that 5 ohm resistor. So we have a 3 amp current there. And again, that current is going to go in on the more positive side and leave on the negative side. So we have a 3 amp current there. Now that gives us the currents through our resistors, but we still don't have the currents through our sources and I sub s. So how do we find those? Well, we need to use Kirchhoff's current law here. So I'm going to start, and it doesn't matter where you start now that we have a few of our currents. You want to find where you only have one unknown. So if we look at C, we know that we have I1 coming in and I2 coming in to IC, and we just don't know what I sub S3 is. So I want you to notice if I1 and I2 are coming in, that means that IS3 is going to have to be leaving. So IS3 would be equal to our 1.2 amps coming in from R1 plus our 1.75 amps coming in from R2 to be a total of 2.95 amperes. Okay, now again, that has to be leaving, and that's not what this directional arrow says. Well, the directional arrow is wrong. Okay, that's what we're saying. Kirchhoff's current law says this current is going to have to be, I'm going to make that red just to stick with the conventions here. That's going to have to be 2.95 amperes in that direction. There's really no other option. It just has to be that way. So I'm going to kind of scratch out that. All right, so now what? Well, that 2.95 amperes continues around this way, and let's look at this ground node right here. I'm going to call it at ground. So we have our 3 amps coming in from R3 and our 2.95 amps coming in from that 8-volt source. So that means that our source current would have to be leaving, well, that's the 20-volt source current. So I source, I guess it's not already indicated with something, so I'm going to put the 20-volt down there just so we're clear on what that is. That's going to be my 3 amps coming in plus the 2.95 amps coming in as well, for a total of 5.95 amps actually going up through or from the 20-volt source. And that's going to continue up through the source. And now I can look at Kirchhoff's current law there at VA. And what do we see here? Well, we've got 1.2 amperes leaving the node, 5.59 coming in, and so we just need this current right here. Now I went ahead and drew it leaving the node just because this 5.95 coming in is larger than my 1.2 leaving, so I know I'm going to need more current that leaves that node. So 5.95 amperes coming in minus 1.2 amperes leaving means that I would have 4.75 amps left over coming down there. Okay, so 4.75 amperes. And just to check, there's one node that we haven't looked at, and that's B. So we've got 4.75 amperes coming into B, and then the other currents are leaving, so they should be on the other side of the equation, 1.75 and 3. And if we have done everything right, these should be equal. 4.75 equal to 1.75 plus 3. They are equal. Therefore, we have done something right in working out this problem. So now we have all of the voltages, all the voltage drops in the circuit, and all of the currents labeled with their correct direction. And this was just an example of doing some circuit analysis that required, instead of doing reduce and return, it required us to lean very heavily on our Kirchhoff's voltage law and Kirchhoff's current law. When we move on to mesh and nodal analysis, this is going to be even more important that we apply these laws correctly. So go back over this video if you need to, and let me know if you have any questions.